In this video, we're going to learn about concentrations, which are one of the main measurements that we use in chemistry. So first, what are concentrations? Well, concentrations are the number of something that is in an amount of space. So one way we can think about this is if we make a box, and if we put a few balls in the box. So let's put 5 here. Then the concentration of balls in the box would be 5 balls per 1 box. So here with our arbitrary units, the concentration would be 5. Now let's say we added a second box and put 3 balls in it. Now for this whole system, we have 8 balls total and 2 boxes. So now our concentration would be 4. When looking at these concentrations in the context of chemistry, there's 4 main forms of measurement that we use. And the first that we'll talk about is molarity, which is often abbreviated as a capital M. So molarity is defined as the moles of solute divided by the volume of the solution. And the units of the solution must be liters. So our total units here would be moles per liter. The next that we often use is percent mass, which is often denoted just with a percent sign. And percent mass is our grams of solute for every 100 grams of our solution. Another unit we use is parts per blank, and usually that blank is million or billion. And this is often denoted as ppm for parts per million or ppb for parts per billion. And this is defined as the grams of solute divided by whatever our blank is. So here either million or billion. And so that can be 10 to the 6th power grams of solution, or it can be 10 to the 9th for billion. And so the units for these, since we have grams of solute divided by grams of solution, is going to be grams over grams. And so for million, oftentimes we use micrograms per gram, since there are 1,000,000 micrograms in 1 gram. And for billion, we use nanograms per gram, since there's 1,000,000,000 nanograms for 1 gram. And the last one we should keep in mind here is mole fractions. And the mole fraction, just like it sounds, is a fraction of the moles of solute divided by the total moles. So a good way to think about our mole fractions is if we go back to the box analogy. So let's say in our box we have 4 white balls and we have 3 green balls. Now here our mole fraction of green balls would be 3 green divided by the total number, which is 7, which would give us a mole fraction of 3 over 7. And then for the white balls, we would have 4 white divided by 7 total, so the mole fraction would be 4 over 7. So now let's do some examples. So here we're given 0.3 moles of HNO3 in 100 milliliters of H2O. So molarity is equal to the moles of solute divided by liters. So here we're given our solute as HNO3, and we have 0.3 moles. So that will go on the top of our fraction. Now we have 100 milliliters as our total volume. And so first we need to convert our 100 milliliters to liters. So 100 milliliters times 1 liter over 1,000 milliliters. Now our milliliters will cancel out, and that gives us 100 divided by 1,000, which is 0.1 liters. So now we can plug that into our molarity equation, so 0.1 liters, and we get 0.3 moles divided by 0.1 liters, which is 3 molar HNO3. Let's do another example. So here we have to find the percent by mass, and we're given 1.125 grams of sucrose in 75 grams of solution. So to find percent by mass, we take our mass of our solvent and divide it by the total mass, which here we're given is 75 grams. And then since we're finding a percent, we have to multiply by 100. And this will give us 1.5% sucrose in our solution. This example is a little bit harder. A solution is prepared by dissolving 18 grams of glucose in 234 grams of water. The total final volume is 250 milliliters. Find molarity and percent by mass. You can pause the video to try to solve it on your own. So first, let's remind ourselves what we're trying to solve for. So first we want to find molarity. And remember, molarity is the moles of solute divided by the volume of the solution. And so those are the two things we'll have to find. So first, we're given the volume of solution is 250 milliliters. So to convert milliliters to liters, we can divide by 1,000. So here we get 0.25 liters. And now we want to convert from grams of glucose to moles of glucose, since glucose here is our solute. So the chemical equation for glucose is C6H12O6, which might be helpful if you were trying to solve this on your own. So to find the molar mass, let's remind ourselves that we have 6 carbons, and each carbon has an atomic mass of 12. So 6 times 12 is 72. We have 12 hydrogens with atomic masses of 1, so that's a total mass of 12. And then we have 6 oxygens with atomic masses of 16, so that's a total mass of 96. And if we add those up, we should get a molar mass of 180 grams per mole. Now we have 18 grams of glucose, and our molar mass of glucose is 180 grams per mole. So that means if we're using dimensional analysis, we want grams on the bottom and moles on top, so that our grams will cancel out. And so we have 180 grams for every 1 mole. And so 18 divided by 180 is 0.1 moles of glucose. Now we can put that back into our equation up top. And 0.1 divided by 0.25 is 0.4 molar glucose. And so that's the molarity of our solution. Now we also have to find the percent by mass. And let's remind ourselves that the percent by mass is grams of the solute divided by 100 grams of the solution. And so if we're really trying to calculate this, the easier equation is grams of solute divided by grams of solution, and then we can multiply by 100. So in this case we need the grams of solute and the grams of solution. We're given the grams of solute is 18 grams of glucose, and then for our total grams of solution we have 18 grams of glucose plus 234 grams of water, which gives us 18 divided by 252 times 100. And if we plug that into our calculator, we should get 7.14% glucose by mass. The next example, in a chamber there are 5 moles of O2, 15 moles of N2, and 5 moles of CO2. Find the mole fraction of each gas. So we want to solve for O2, N2, and CO2. And so our mole fraction is the moles of the solute divided by the total moles. So for O2, we have 5 moles of O2, and then we have 5 moles of O2 plus 15 moles of N2 plus 5 moles of CO2, which is 5 over 25. And these are often written as decimals, so our mole fraction would be 0.2 oxygen. Now for N2, we have 15 moles, again over 25 total, which would equal 0.6 as our mole fraction for N2. And then for CO2, similar to O2, we have 5 over 25, which equals 0.2 as our mole fraction for CO2. And a good way to check that your mole fractions are correct is that all of our mole fractions should always add to 1, because our total moles is represented as 1. So here 0.2 plus 0.2 plus 0.6 does equal 1, so our answer is likely correct. You can pause the video to try to solve this next one on your own. Now, depending on where you've gotten in your chemistry course, you may have used the equation M1V1 equals M2V2, which is the dilution equation, and that's probably the easiest way to solve this. But since this is a concentration video, we'll be solving it without that equation. So first we need to find the number of moles of HCl, because we want the molarity for the final solution. So remember, molarity is moles divided by liters. So first we need to find the moles of HCl. So we're given that for HCl we have a 1 molar solution, and so we want to know the number of moles, and then we're given 10 milliliters. And so converting our 10 milliliters to liters, since there's 1,000 milliliters per liter, gives us 0.01 liters. So let's substitute that in. Now if we solve for X number of moles, we get that there is 0.01 moles of HCl. Now if we plug that into the top of our equation back at the start, we have 0.01 moles of HCl, and we want to know the total volume. So the total volume of our solution will be the 10 milliliters of HCl that we added plus the amount of water. And since water has a density of 1 gram per milliliter, we can always switch out the grams for milliliters without changing the number. So here we have 500 milliliters of H2O. And so if we add those up, our total solution is 510 milliliters. And then converting that to liters, we can divide by 1,000, and we get 0.51 liters of solution. So plugging that into the start, we have 0.01 moles of HCl divided by 0.51 liters of our solution. And if we plug that into our calculator, we should get 0.0196 molar. And since it looks like we have two significant figures from the 10 milliliters, we can say that the final concentration will be 0.02 molar HCl. For this last example, we'll do a bit of a more fun application. So we're given an 8-ounce cup of coffee, which is 237 milliliters, and told it has 80 milligrams of caffeine. Find the caffeine concentration in molarity. So to find molarity, we need, again, the moles of the solute and the total liters. So a cup of coffee is 237 milliliters, and like before, we can divide that by 1,000 to get the liters. So we'll have the moles of caffeine divided by 0.237 liters of coffee. Now for the moles of caffeine, we're given milligrams, which is similar to grams. So to convert from milligrams to moles, we need the molar mass. So we're given the molar mass here, which is 194.16. And so let's start with our 80 milligrams. Now doing dimensional analysis, we want to get to grams, so we need to cancel out our milligrams. And there are 1,000 milligrams in 1 gram. And then, now we're in grams, so we want to cancel out our grams on the bottom and have moles on the top. And that's where we use our molar mass. So our molar mass is 194.16 grams per mole. And if we plug this into our calculator, we should get 4.12 times 10 to the negative 4th moles of caffeine. So now, if we put that into our initial equation, 4.12 times 10 to the negative 4th, and plug that into our calculator, we should get 0.0017 molar caffeine in 1 cup of coffee. For the second part of the problem, we're given a 70 kilogram person drinking 2 cups of coffee. What part composition of their body is caffeine in parts per million? So at the beginning, we said that parts per million is often written as micrograms per gram. And so the key when looking at these units is we know micrograms is 10 to the negative 6th, and grams is 1, so that's just 10 to the 0. And so here the top and bottom are 6 orders of magnitude apart. And so we're given milligrams for our caffeine, so if we put milligrams on the top, that's 10 to the negative 3rd. And so kilograms is 10 to the positive 3rd, and that's also 6 orders of magnitude apart. So therefore, milligrams per kilograms is also equal to parts per million, because they're a million apart. 10 to the negative third and 10 to the third. They're 6 orders of magnitude apart. So now we can just plug that in. So 2 cups of coffee would be 2 times 80 milligrams, which is equal to 160 milligrams of caffeine consumed. And their body is 70 kilograms. So if we divide that, we get 2.3 milligrams per kilogram, which is equal to 2.3 parts per million. Now for caffeine, this might seem like a lot, but we can also convert this to a percent by mass by multiplying by a million, dividing by a million, and then multiplying by 100. And if we do that, we get 0.00023% caffeine by mass. So really, after drinking 2 cups of coffee, very little of your body has turned into caffeine.